All right, let's jump right in. Sometimes the biggest breakthroughs in science and math aren't found in a flashy lab, but scribbled in the private diary of a genius. Today, we're going to crack open a page from the journal of the one and only Carl Friedrich Gauss, and you'll see how a seemingly simple calculation led him to a discovery that would literally change the course of mathematics.
And here it is, May 30th, 1799. Gauss writes that something he just figured out will surely open an entirely new field of analysis. I mean, that is a seriously bold claim, right? Not just a new theorem, but a whole new field. So what on earth could he have found that was so huge? Well, the journey to figure that out starts with two numbers that are, you might be surprised, incredibly simple.
And there they are. The two numbers that kicked off this entire revolution were just 1 and the square root of 2. That's it. It's almost hard to believe. How could these two numbers that we see all the time be the key to a whole new branch of math? Well, the genius wasn't in the numbers themselves. It was in what Gauss did with them.
He used this really elegant and, believe it or not, surprisingly simple algorithm to mash them together. And I'll pop this single, new, and pretty mysterious number. Let's walk through exactly how he did it, step by step.
The whole process is called the Arithmetic-Geometric Mean, or AGM for short. The idea is pretty cool. You start with two numbers, and then you create two separate sequences from them. For one sequence, you just keep taking the average. That's the arithmetic mean. For the other, you take what's called the geometric mean. The magic, the real trick, is seeing where these two paths eventually lead.
Okay, so here's the nuts and bolts, and you'll see just how straightforward this is. You take your two numbers. For us, that's 1 and the square root of 2. Step 1, find their average. Boom, that's your new first number. Step 2, find their geometric mean, which is just a fancy way of saying multiply them together and take the square root. That's your new second number. And then you just do it all over again with your new pair of numbers. Repeat, repeat, repeat.
And check this out. These are the actual numbers from Gauss's work. Column A is the average, the arithmetic mean, and column B is the geometric mean. Just look at how fast they start sprinting towards each other. After just one round, they're already pretty close. By round 2, they're starting to look like twins. And by the third round, bam, they're practically identical. It's an incredibly rapid convergence. And this is the destination. This is the number that they both agree on, the single value they converge to, the arithmetic geometric mean of 1 and the square root of 2. It's this beautiful, precise, specific number that Gauss himself calculated out to a mind-boggling number of decimal places.
So, we did it. We have our number. But that just brings us right back to the big mystery, doesn't it? What does this number actually mean? Why was finding this number so important that it made him predict a whole new era of math? Well, the answer, it turns out, isn't found in arithmetic, it's found in geometry.
This is where things get really wild. Gauss had this flash of insight and realized that his number, this purely abstract calculation, was secretly describing a property of a very specific and very beautiful geometric shape.
And this is the shape. It's called the lemniscate of Bernoulli. It was first described way back in the 1690s, and I love this. It was poetically called a knot of a French ribbon. It's this perfect little infinity symbol, a figure 8 curve. So, what in the world does this ribbon have to do with Gauss's number?
Well, the secret is in its length. If you were to trace the full length of this curve, the total distance you travel is tied to a fundamental mathematical constant. And Gauss, being Gauss, even gave it his own special symbol. He called it varp, which looks like a variation of pi. This was his lemniscate constant. And here it is, the punchline. The number Gauss got from his simple little algorithm was exactly equal to pi divided by his lemniscate constant. This is just incredible. A process from pure arithmetic was perfectly describing a fundamental property of a geometric shape. No wonder he was excited. But get this amazing discovery still wasn't the new field of analysis he was talking about. That was yet to come.
Yeah, that lemniscate connection was absolutely profound, but it was really just the tip of the iceberg. The true revolution, the entirely new field, was born when Gauss decided to take his simple algorithm and push it into a much weirder and wilder territory. He asked one of those simple, earth-shattering, what-if questions. What happens if the numbers you start with aren't just regular old real numbers? What if you plug in complex numbers? You know, numbers that have an imaginary part?
And the result was chaos. The whole thing just exploded. That one clean, single answer that the algorithm always gave before,
It shattered. Because the square root of a complex number can have two different values, the AGM didn't just go to one answer anymore. It branched out over and over, creating an entire infinite family of possible answers. Now, you'd think he'd be frustrated by this, right? But listen to what he wrote a year later. He said that discovering this web of infinitely many answers and seeing how they were all connected was a source of happiness for us. He wasn't seeing a problem. He was seeing a beautiful, infinite new world to explore. This was what he had been looking for.
So how do you even begin to navigate an infinite world of answers? You can't use the old maps. You need new ones. And to do that, Gauss had to basically invent a new kind of mathematics. This is it. This is the entirely new field of analysis he promised.
See, the challenge wasn't about finding one right answer anymore. It was about understanding the structure of this whole infinite landscape of interconnected answers. It had this hidden, beautiful repeating pattern. And to describe that pattern, Gauss had to forge completely new mathematical tools, things we now call theta functions, which were powerful enough to describe these infinitely complex patterns. And this is what grew into his new field. By chasing down the solution to the complex AGM, Gauss laid the groundwork for the theory of theta functions and modular forms. These are hugely important ideas today that connect arithmetic, geometry, and complex numbers in deep, profound ways. He didn't just solve a problem. He built the language and the tools for a whole new mathematical universe, basically anticipating 100 years of progress.
And to think, it all started with just two numbers, 1 and the square root of 2, and a simple little process you could do with a pencil and paper. It just makes you wonder, doesn't it? How many other revolutionary ideas, how many other entirely new worlds are still hiding right under our noses, inside the simplest things we think we already understand?